there. Sketch a scatter plot for each. I'm actually excited because I changed the format of these questions on the quiz, so it'll be good this year. Sketch a scatter plot for the pair of variables indicating what association you would expect, just like we did on the homework. Be sure to label the axes and estimate the correlation coefficient. All right, so the number of miles a student lives from school and the student's GPA average. So if you live closer to school, is that going to improve your GPA or make your GPA worse? Probably not. So we're going to be expecting just random scatter, right? So there's really not going to be any association here. But before we do that, what is our explanatory variable? So are we using miles from school to explain GPA or GPA to explain miles from school? Well, probably what we're interested in measuring is actually the GPA, and the explanatory variable would be miles from school, okay? So again, as we increase in miles, we get further away from the school, does not mean our GPA goes up or down. So the direction is going to be neither. The form, this is not linear or exponential or sinusoidal. There's really no form here, so you can just say none. The strength is going to be, it's not a weak association. There's really no association going on here. So our correlation is going to be close to 0. And our strength would just say there's no association, so it's not even a weak association. There's nothing going on here. These are not the droids you're looking for. Part B, a person's blood alcohol level, BAC, and time it takes for them to solve a maze. So it's kind of funny. All right, so what we're going to be looking at is as the blood alcohol content increases above the legal limit, then how long does it take them to solve the maze? So I'm actually going to write this one vertically like that. Oops, not what I was trying to do. Okay, so as we increase in blood alcohol content, what's going to happen to the amount of time it takes you to solve the maze? Well, it's going to go up. So the direction is clearly going to be positive. The only question you might have is it going to be linear or is it going to be exponential? So as you get past a certain point, the alcohol was probably going to have a greater effect until you can't even solve a maze at all. So this would probably be exponential, right? So with lower blood alcohol content levels, you might not have as much of an effect, but as it increases and gets to a point that you're not going to function, and that's why you don't drive. All right, so the form I'm going to say is exponential. If you went with linear on these, I'm pretty forgiving because sometimes, you know, how you think through it, some people think through it differently, right? All right, and then strength. On this one, there is going to be variation from person to person on how they react to higher blood alcohol content levels. But so I would say maybe this would be moderate or maybe moderately strong association. And the correlation, the problem with the correlation here is because we're calculating it. Actually, let me pause the video and I'm gonna doctor this image up real quick for you. All right, so what I did here is I graphed out the mean point, so like the average blood alcohol content and the average amount of time it takes to solve a maze. So what you notice here is that if this was linear, it would pass through that mean point, okay? But it's actually not going to pass through the mean point because it's curved, okay? So what's going on here, instead of being entirely positive, where all these points, most of the points would be positive products of the z-scores, we're going to have this part here that's going to be negative. And so these negative ones down here are going to counteract some of the positive ones in these two quadrants. So our correlation coefficient is going to be weaker than what it would actually be if we re-express the data first. So instead of a moderate one of having like 0.8 or 0.75, this one's going to be even weaker than that, maybe even 0.6. But remember, the correlation coefficient is not an appropriate measurement of the strength of a curved association. This is the appropriate measurement of strength if it was a linear association, which it's not. So anyway, that's why our correlation coefficient would be less than what you would normally see if you saw that amount of variation among that's about a line instead of a curve. Okay, so careful with that. All right, weekly sales of hot chocolate in Montana diner and the number of car accidents in the week in the town. All right, so we're gonna say I'm interested in measuring the car accidents, and I'm going to go with the hot chocolate sales. There's actually a lurking variable going on here if you're wondering why this sounds totally random. So think about Montana, think about driving in Montana. What causes car accidents? What about their winters, right? When do you eat hot chocolate? Probably during the winter time, right? So as the temperature drops and people are buying more and more hot chocolate because they're cold, the road conditions are probably going to get worse, and so there's going to be more car accidents, right? So I'm expecting this to be positive. The form, you could say linear. I would go with that. That's fine. Maybe it'd be exponential, but maybe at some point it gets so cold people stop driving and stop eating hot chocolate or going to the diner. I don't know. You can think about it until, you turn blue in the face until the cows come home. Oh, I love idioms. They're so much fun. All right, anyway, so I went with linear, apparently. I thought there was going to be quite a bit of variation because it's not like really strongly connected to each other, but that's okay. So form, I said, was linear. You could have gone with exponential. Honestly, it's fine. Strength, it's going to be I said moderate. Because this is linear and moderate, it might be close to like 0.7 for a correlation coefficient, where this one had a stronger one, but it was actually 0.6. You see that? See, this was a stronger association, but it wasn't linear. Okay, hopefully you understand that. All right, so we pretty much did that one. No big deal. So much fun. All right, next one. Hours spent studying and the number of problems missed on a test. So I'm going to say number of problems you miss is what I'm interested in measuring. And then hours spent studying is going to be our explanatory variable. So as you increase the number of hours that you spend studying, the number of problems you miss should be going down. So our direction would be negative. The form, I'm going to think that it's going to kind of level off after a while. So if you studied 10 hours or 10 hours and then you study 20 hours, it's not going to be half from that point. So it's probably going to be exponential just by nature. So I thought it looked something along the lines of that. So it is exponential, kind of like a reciprocal or an inverse. And then the strength I thought would be fairly strong. And then the correlation, again, because we're measuring correlation here, but it's not linear. If I do the mean point here, all these points down here are going to counteract these points here. So it might actually show it being closer to 0. So maybe like negative 0.8, I guess, instead of like 0.9 or 0.95. So this actually would probably be even lower depending on, except I didn't graph those points out very well. So anyway, you get the idea. All right, let's see, amount of rainfall during growing season and the crop yield in bushels per acre. So rainfall, I'm going to put that as my x-axis for the explanatory. Crop yield, that's going to be on the y-axis. So as we increase in rainfall, we're going to have more crop yield. I thought this one would be exponential, and the reason for that is rainfall is measured in 1 dimension, but crop yield is 2 dimensions because it's area. So it is going to be exponential. It's going to increase, like y is equal to x squared because it is squaring it essentially. Direction is positive, form is exponential, strength is going to be fairly strong. But the other problem here is that it's not just the rainfall. You could actually have too much rainfall, and it also matters about the temperature. So if it's too cold and you don't have enough sun, then crops will fail for lots of very different reasons. It's not just about rainfall, but in general you would expect it to increase. So I guess I said about positive 0.75. All right, local university, every student gets a college email address. Data collected by the college showed a negative association between students' grades and the number of emails a student sent during the semester. Briefly explain what a negative association means in the context. So negative association means that as the explanatory variable increases, we expect the response variable to decrease. So just like over here, this would be a positive association because as the drop increased, the speed increased, but as interest rates went up, the number of mortgages they did went down. So negative association means that in general, the more emails a student receives, the lower their grades. So I'm careful not to imply a causal relationship, meaning that, well, we'll do that on the next one. Okay. After seeing the study, college proposes trying to improve academic performance by limiting the amount of emails. I'd be all for that. Sounds great. Email students send throughout the college address or whatever. As a statistician, what do you think? Again, remember, correlation is not equal causation. So just because there was association between the two doesn't mean there's not a lurking variable or that you even know which direction it's actually going in. So yeah, correlation is not equal causation. Same thing, remember the storks. That's not where babies come from, right guys? Okay, number 10. Local bookstore owner wanted to examine if there was an association between the number of employees he had working sales and the amount of sales that he actually did in thousands of dollars. He recorded the data for 10 days shown in the table to the right. Sketch scatter plot to the right and describe the association. So with your calculator, we're going to put in all the data here. The number of sales is going to be, yeah, number of sales people working or employees working in sales, whatever. That's going to be our explanatory variable, and the response variable, which is what we're actually interested in, is the sales in thousands of dollars. So I'm going to go to stat, edit, and I have it all here. Make sure that you don't have any typos because that can mess you up. And there were 10 of them all together, so we're good to go. Then I want to graph a scatter plot. So I'm going to make sure I only have one plot on. Scatter plot, list 1 is our explanatory. That was the number of people in sales. List 2 is the actual sales themselves. And then we're going to hit zoom and 9. Graph that out. Oops, spoilers, you're not supposed to see that. There we go. So there's our association. Boom, scatter plot. Done. So you can graph it out rough. Make sure you also label your axes, of course, because that was one of the most common mistakes I had on the test for Unit 1. All right, sketch scatter plot to the right, describe association. All right, so it's going to be positive. It looks like it is linear. It actually is linear, and the strength is going to be moderately strong. Okay, what is the explanatory variable? Well, that's going to be the sales of the employees that are working in sales or on the sales floor, however you want to describe it. Is it appropriate to summarize the strength of the association with the correlation coefficient? Yes, because we're dealing with quantitative data. There's no outliers, and it is actually linear, so we're good. Is it appropriate to summarize? Yes, that's what I just said. All right, write a model to predict the sales. So to get the model, we have to go to stat, and we arrow over to calculate, linear regression, which is the 4th option. We can just hit 4. We're going from list 1 to list 2. I'm going to go ahead and store the regression equation because we're going to use it later as variables, y variables, function y1. Then hit calculate. And it stored it as y1 in case you're wondering, and it'll turn it on automatically. So if you hit graph again, there's your function. And if we hit trace, which is right here, you can either trace the points themselves, or if you arrow up, you can trace the actual function. Arrow down, back to the points. Kind of cool. All right, where was I? So second quit. I did want the linear regression, so I'm going to go ahead and run that again. All right, so that's going to give me my correlation, my coefficient of determination, and the slope. So ax plus b, so a is the slope, b is the y-intercept. Okay, so if I want to write the actual, model itself, that looks like this. So sales hat, so the predicted sales is equal to our slope times the number of employees that are working the sales floor plus our y-intercept, which is 8. In that case. All right, so write a model, predicted sales in thousands of dollars. That's what we did, no big deal. Explain in context what a slope means. So our slope says that for every additional employee, that on average our model tends to show that for every additional employee working the sales floor, we would expect to have $913 of increase in sales. Okay, explain in context what the y-intercept. So if we had no employees working sales, so if this value was 0, so if we plugged in 0 for that, then we would expect, even if we had no employees working sales, we would still expect to make $8,000 or $8,100 in sales. All right, sketch the plot of the residuals. So every time that we create a linear regression, it will store the residuals and the residual plot, which is, you can find that by going to second list, and an arrow to the bottom will be the residual plot. So I want to graph that out across the y-axis. So that's going to be our new response variable, which is what we're actually interested in. So that's the actual minus the predicted. So again, go to second, stat to list option to the very bottom, residuals, and that's it. So then we go to zoom 9. I'm going to go ahead and turn off my model because otherwise it's going to be annoying. So zoom 9, boom, there it is. Okay, cool. So that's the plot of the residuals, no big deal. And while I'm here, might as well, this is kind of nice. If you go to trace, you can actually see the actual points themselves. So that when we had, so this would be 2 employees working sales, 3, 7, 9, 10, 2 values for 10, 12, 14, 16, 20, all that good stuff, okay? So that's actually kind of helpful because then the Y value is the residual, which tells us that we were $715 less than we would expect when we had 16 people working sales. And then this one over here, when we had 10 people working sales, we were $2,765. We sold that much more than we expected. Anyway, positive residual is the points on the top, the bottom residuals are the one on the bottom, and they average out to 0, by the way, in case you're curious. Or they add up to 0. All right, what is the coefficient of determination R? So that was found earlier. You can also take the correlation and square it. If you need to find that value again, you can quit out of this. So second quit, and then go up and rerun your linear regression. And that's it. Okay, so the basically correlation coefficient squared is going to give us the coefficient of determination. Okay, so that's that value. Explain what it means in context. So this is the percent of the variation that can be removed in the response variable by our model with the number of employees. Okay, so in other words, 96.53, that's not right. So 96.32. 93.2, gosh, you get the idea. All right, so 93.2% of the variation in sales can be accounted for by the model with the number of employees working the sales floor. Calculate the residual for the day where they had 9 employees working and made 14,000 in sales. So we need to use our model, and we want to evaluate our model. So best way of doing that is, so I'm going to quit out of that, and I'm going to go to variables, y variables function y1, and I'm going to evaluate this for 9 employees to see what the model would predict. And then the actual they said was 14, so the formula that we use is going to be RAP, so residuals is equal to the actual, there we go, the actual minus the predicted. So the actual amount they said was 14,000, and our predicted amount was that value, the 16. So I'm going to do 14 minus whatever the predicted amount was, which is going to give me a negative 2.32, but remember this is in thousands, so we move the decimal 3 places. So essentially we get 14 minus that, which is going to be negative $2,321. What in this context was a negative residual mean? Well, that means that we sold less than we expected. So that's all that a negative residual means. I think we're done. We are done. Cool. Not what I was trying to do. Okay, so we're done. I'm going to break this up into 2 videos because that just makes it much more easier to digest. We'll just put it that way. Then you can take breaks in between the 2. So anyway, tomorrow we'll take the quiz itself. So you guys have the solutions to the practice quiz. If you have any questions, again, I'm always on Google Meets from 1 o'clock to 2 o'clock. So feel free to reach out and ask. And I'll see you guys later. Have a good day.